Hey friends, welcome to the YouTube channel All About Electronics. So in this video, we will learn how the astable multivibrator can be designed using the BJT. But before that, first of all let us quickly see what is astable multivibrator. So in an astable multivibrator, there is a no stable state. That means the output of the circuit continuously changes between the two states. And here, the duration for which the output remains in a one particular state can be controlled by the passive elements like the resistor and the capacitor. So now let us see how the astable multivibrator can be designed using the BJT. So this is the circuit of the astable multivibrator, and as you can see it consists of two transistors. So this is the first transistor and the corresponding base and the collector resistors, while this is the second transistor. And as you can see, both transistors are cross coupled. That means the collector of one transistor is connected to the base of the other transistor using this capacitor. So now let us understand the working of this circuit. And before we understand the working, here I am assuming that you are aware of how the transistor acts as a switch. That means when the input to the BJT is less than the 0.7 volt, then it will operate in the cutoff region and it will act as an open circuit. And at that time, this voltage VCE is approximately equal to VCC. Similarly, when the input at the base is high, then it will operate in the saturation region. And at that time, it will act as a short circuit. And in this saturation region of operation, the voltage VCE is approximately equal to 0 volt. Now the reason I am telling this is because while understanding the working of this astable multivibrator, we will replace these transistors either by a short circuit or the open circuit based on the region in which they are operating. So initially, when the supply is not given to this circuit, then both transistors will be in the off condition. And as soon as we apply this supply voltage, then both transistors will try to conduct. Now one more thing to notice over here is that the value of this collector resistor is smaller than the base resistor. So as soon as we apply the supply voltage, then the capacitor starts charging through these paths. But due to the mismatch in both circuits, one transistor will conduct more than the other one. And due to that, only one transistor will go into the saturation first. Now here, any of the two transistors can go into the saturation first. But let's say here Q1 goes into the saturation first. And due to that, the collector emitter terminal of this transistor will act as a short circuit. Now up to this point, when the transistor Q2 was conducting, then let's say some charge got accumulated across this capacitor. And due to that, let's say the voltage across this capacitor C1 is equal to VC1. But as soon as this transistor Q1 goes into the saturation, or due to this short circuit, the left hand side of this capacitor will get grounded. Or we can say that due to that, the voltage minus VC1 will appear across this transistor Q2. So due to this negative voltage, this transistor Q2 will go into the cutoff region. So this is the starting point of the circuit. That means as soon as we power up the circuit, then one transistor will become on while the other will remain off. And here we are assuming that the transistor Q1 will become on and the transistor Q2 will remain off. That means transistor Q1 will act as a short circuit while the transistor Q2 will act as an open circuit. And due to that, the voltage at the collector of this first transistor will be equal to 0 volt, while the voltage at the collector of the second transistor will be approximately equal to VCC. So these are the 2 points where we will get the output of this astable multivibrator. And as you can see, both outputs will be opposite to each other. So let's say this point is Q, then this point is Q bar. So this is the first state of the astable multivibrator. That means the transistor Q1 is on and the Q2 is off. Now let's see how the change in the state occurs, or how this output goes from the low voltage to the high voltage. Now in this state, this capacitor C1 reverse charges or charges in the other direction, and it will charge through this resistor RB2. On the other end, this capacitor C1 will charge through this resistor RC2. Now if you notice over here, this transistor Q1 is in the on condition. So the base emitter junction of this transistor will be forward biased, and typically the voltage across it will be equal to 0.7 volt. That means the left hand side of this capacitor C2 will be at the 0.7 volt. So we can say that this capacitor C2 will get charged up to the voltage VCC minus VBE, or to be precise, the voltage VCC minus VBE of this transistor Q1. But here we are assuming that for the both transistors the value of VBE is same. On the other end, this capacitor C1 starts charging towards the voltage VCC. Now one more thing, if you notice, here this collector resistor is smaller in value compared to the base resistor. So this capacitor C2 will charge faster than the C1. And as soon as the voltage across this capacitor C1 becomes 0.7 volt, then the same voltage will also appear at the base of this transistor Q2. Because here this transistor Q1 will act as a short circuit. So due to that, this transistor Q2 starts conducting and eventually it will go into the saturation. And hence this transistor Q2 will act as a short circuit. Meanwhile, this capacitor C2 is already charged up to the voltage VCC minus VBE. And as soon as this transistor Q2 gets short circuited, then the right hand side of this capacitor C2 will get grounded. That means now the voltage which appears at the base of this transistor Q1 is equal to minus of VCC minus VBE. So due to this negative voltage, this transistor Q1 will get turned off. That means now the transistor Q1 is off and the Q2 is on. So this is the second state of the multivibrator. That means now over here the collector voltage will be equal to VCC, while at the other end it will be approximately equal to 0 volt. That means now at this end the output has gone from the low value to the high value, while at the Q bar output the output has gone from the high value to the low value. So now let us see once again how the transition will occur at the output. That means how the output will go from the high value to the low value. So in this condition, when the Q1 is off and the Q2 is on, then this capacitor C2 charges in the reverse direction through this resistor RB1. While on the other end, this capacitor C1 will charge through this resistor RC1. So this capacitor C2 will charge towards the voltage VCC, while this capacitor C1 will charge up to the voltage VCC minus VBE. So here, as soon as this capacitor C2 charges up to the 0.7 volt, then the transistor Q1 will start conducting, because this voltage will directly appear at the base of this transistor Q1. So eventually it will go into the saturation, or we can say that this transistor Q1 will become on, and due to that it will act as a short circuit. So up to this point, this capacitor C1 has charged up to the voltage VCC minus VBE. And now due to this short circuit, the left hand side of this capacitor will get grounded. So we can say that the voltage minus of VCC minus VBE will appear at the base of this transistor Q2. So due to this negative voltage, this Q2 will turn off. So in this way, the state of the multivibrator has changed once again. That means now the Q1 is on and the Q2 is off. And if you see the output over here, and once again there will be a transition from high to the low. And similarly, if you see the output at the other side, that means at the Q bar, then it will be exactly opposite. So in this way, the output of the multivibrator changes continuously between the high and the low state. And if you see the output at the other side, that means at the Q bar, then it will be exactly opposite. So here the charging of the capacitors decides the on and off time of the multivibrator, or to be precise, the RC time constant RB2 times C1 and the RB1 times C2 decides the on and off time as well as the frequency of this multivibrator. So now let us derive the expression of the on and off time and the frequency of this astable multivibrator. So here for the derivation, let us assume that initially the output Q is low, and after time t1 it goes to the high state. So whenever the Q is low, then we can say that this transistor Q1 is in the on condition. So due to that, this capacitor C1 will charge through this resistor RB2, and once it gets charged up to the 0.7 volt, then there will be a transition in the output. Also, one more thing to note down over here is that before the capacitor starts charging in the reverse direction, the voltage across the capacitor C1 was VCC minus VBE. So now, to find this time t1, let us write down the general expression of the voltage across the capacitor. So the voltage across the capacitor Vc of t can be given as Vc of infinite plus Vc of 0 minus Vc of infinite times e to the power of minus t divided by Rc. Now we have already derived this expression in the earlier videos of the transient analysis. So for more information you can check that video. But here, to get the value of this time t1, let us note down the values of the initial voltage as well as the final voltage across the capacitor. So here, the initial voltage Vc of 0 across the capacitor is equal to Vcc minus VBE. But the polarity of this voltage is reverse. So we can say that the initial voltage across the capacitor is equal to minus Vcc plus VBE. Similarly, this capacitor C1 charges towards the voltage Vcc. That means if capacitor charges fully, then the voltage across this capacitor C1 should be equal to Vcc. That means we can say that Vc of infinite is equal to Vcc. But here we are interested in finding this time t1 when the voltage across the capacitor reaches the 0.7 volt, or in other words it will be equal to VBE. So let's say at time t is equal to t1, this voltage Vc of t1 is equal to VBE. So to find this time t1, let us put all these values into this expression. That means we can say that voltage VBE is equal to voltage Vcc plus minus Vcc plus VBE minus Vcc times e to the power of minus t divided by Rc. Now here the value of R is equal to RB2 while the capacitor C is equal to C1. So if we further rearrange this expression, then we can say that e to the power of minus t divided by RB2 times C1 is equal to voltage VBE minus Vcc divided by voltage VBE minus 2 Vcc. Now here, for this circuit to work, the voltage Vcc should be much larger than the VBE. And usually that is the case in the circuit. So usually in the circuits, the voltage Vcc is much larger than the VBE. So assuming this condition, we can say that e to the power minus t1 divided by RB2 times C1 is equal to minus Vcc divided by minus 2 Vcc. Or if we take the natural log, then we can say that this time t1 is equal to minus RB2 times C1 times natural log of 1 by 2. Or we can say that this time t1 is equal to RB2 times C1 times natural log of 2. So this will be the expression of this time t1. Similarly, this time t2 can be given as RB1 times C2 times natural log of 2. So the total time period t is equal to t1 plus t2, which is equal to RB2 times C1 plus RB1 times C2 times natural log of 2. Or we can say that this time t is equal to 0.693 times RB2 times C1 plus RB1 times C2, because the value of natural log of 2 is approximately equal to 0.693. And whenever this RB1 and RB2 are equal, and similarly when C1 and C2 are equal, in that case this time period t is equal to 1.386 times Rc, or approximately we can say that it is equal to 1.4 times RC. Now the frequency f is equal to 1 by T. So if we calculate the frequency f, then roughly it will be equal to 0.72 divided by RC. So in this way, we can get the desired frequency of oscillation for this astable multivibrator. And if the values of resistors and the capacitors are not same, then the on and off time of this astable multivibrator will be unequal. Now for this astable multivibrator, if we see the actual output waveform, then it will look like this. So this rounded curve is due to the charging of the capacitors. For example, when Q1 is off and Q2 is on, then this capacitor C1 charges through this resistor RC1. And once it fully charges, then that voltage will appear at the collector terminal. So due to this charging effect of the capacitor, the waveform will look like this. So by properly selecting the value of this collector resistor, it is possible to improve the shape of the output waveform. And further it can be improved by introducing the diodes in the given circuit. So if you require, then I will provide the separate note for that improved circuit. But I hope in this video you understood how the astable multivibrator can be designed using the BJT. So if you have any question or suggestion, do let me know here in the comment section below. If you like this video, hit the like button and subscribe to the channel for more such videos.